Hi, I'm going to be covering an exam prep section today, so I have to prepare anyway. So I thought that I'd just record myself trying out these problems. And yeah, I think it could be helpful because this is not really me explaining the problems, but just trying out problems I've seen for the first time. And I think especially for tree recursion, sometimes explaining the theory looks a little different than actually solving them. So yeah, hope it helps. So I'm going to try these out. Number one is called aim for 100. We have a function, count subsets, that takes as input a list of positive integers, and it returns a list of lists that sum to 100. So this is actually my year, so I guess I have done this problem, but I don't remember it too well. So we go from a list to a list of ints. Um, And then what must be true about each of these lists? Okay, so we have a list of something. It returns a list of lists. And then for each of these lists, one of the invariants has to be true that they will sum to 100 and contain a subset of the elements of S in order. Okay, so they have to sum to 100. They have to contain a subset of the elements of S in order, which just means that it must comprise only elements taken from that input list S. So comprise things from S. Okay. So yeah, this is definitely giving like count partitions vibes, but instead of counting, oh no, we are counting them. Okay, so this is very count partitions vibes. What's the difference? It returns the number of lists that sum to 100 and contain a subset of the elements of S in order. Oh, is that the difference? Like, have to be in order. Um, so 25 precedes 75, so that's in order. I don't really know how we're defining in order yet. But okay, so I think these annotations do hint that this order is the key thing. But how to differ from competitions? 25. Oh, because there's two 25s. Okay. And 25. Okay, so order is defined in terms of index, not in terms of magnitude or anything. Um, so yeah, so this just means like if we're trying to so for example, so like it's like these would sum 200, but we cannot return 75, 25 because of the ordering thing. Okay. I'm not entirely sure how to solve this yet. But yeah, I do think it's good to just start out a problem and lay out the groundwork and write down what you understand. Um, so because it has to be in order, um, I think there has to be some element of like like sequential access. Like I'm gonna look at each element in order, and through that process, it constrains us to like only possibly forming lists that do comprise um like well-ordered elements. Um, all right, so let's say I have an input list, 45, 50, 75. Um, and because I'm trying to count all of the possible um different combinations of these elements, we do know we're going to go with that tree recursive approach where I look at the head of my list and like, all right, do I want to include you or do I want to not include you? Um, so if I do choose to include you, then right now here I'm looking for a total of 100. Right, just like in your count dollars problem, initially your total starts out as some amount that you want to make change for, and then as you find dollars that can contribute to making that change, your total is going to go down. So if I choose to use the 25, then my total that I'm looking for now is only going to be 75 because I've made some progress towards my goal. And then um, I can choose to include it or not include it. If I do include it, I want to look at the next element and say, do I want the 50 or do I not want the 50? Um, and so on. Yeah, I don't know. This feels pretty classic. Um, I think I'm gonna cheat a little and just looking at the skeleton. I usually do like to frame it out more in my head before I go in. Um, got a little lazy today. So we have a helper function and we have a sum so far. So I know, okay, so they're going to start sum so far at 0. So I know that sum so far is going to climb from 0 all the way up to 100. Um, so instead of like decrementing total like we did, instead they're starting this amount at 0 and it's going to climb up. And we have a index, which will probably help us maintain the ordering condition. These are our base cases. So if A and B return 1, else return this. Um, okay, so these are all identical. So we have to figure out which one is important to us. And we have C and D. So given that we are aggregating two recursive calls, we can map these onto the two choices we have at every single element, either taking the element or not taking the element. So let's try to figure out which one corresponds to which. And the one that corresponds to taking the element is going to increase the sum so far by the element at the particular index. And so that's how we be able to figure it out. Generally, in a recursive function, so you want to call the outer one, so I'm going to cross them out for now. I think it actually is possible, but I really don't understand those kind of problems. It's more likely that we're going to just call the helper. We have a helper, so we can keep track of an additional total, just a motivation, so we can add additional parameters. And we see that sum so far isn't going to change. So this means that C must be the don't include case, and D must be the include case. So what is D going to look like? It's going to look like, it's still going to be a recursive call, but it's going to be sum so far. And I assume that sorry, sum so far plus whatever is at our index. Uh, and then our index is going to increase, I guess. I think this one feels right. So let's compare these two. So this one is going to skip the index forward. It's going to say, hey, I'm not going to choose to use this element, which is why I'm going to preserve my sum at whatever it is currently and do nothing to it. Whereas if I do choose to use it, then I want to include that in my sum. Now, here, do we actually want to increment the index? Let me think. So are we allowed to repeat elements is the question I want to ask, because that's what this controls, right? If I do not increase the index, then that means I can reuse 25 and then 25 and 25. So is that a possibility? Um, I don't think so. Yeah, because 25, 25, 25 is not an option. So I do think it is probably index plus one. Okay. All right, so going back to what I feel like our algorithm is we have a list, we start out as head, and then for every element, we present the two possible choices. I can either include this element or I cannot include the element. If I do, then my sum so far is going to increase. If I don't, then my sum so far is going to stay the same. And then I think regardless, I'm going to start looking at the next element. And actually, I think their additional condition of the ordering is actually going to make it easier for us just because by asking for us to order it, then that means I don't have to look at these past elements. I can just recurse on this, um, only looking forward. And because we're progressing down the list, and um, like the elements at the end at the beginning can only must be added before the elements at the end, ensuring the whole ordering thing. I feel. I hope. All right. So there's two stopping conditions that feel natural, right? So given that my algorithm is all about indexing through my list, I suppose that once my index hits the end, I should probably stop recursion. And it's also true that the success case is when my total is when my sum so far hits 100 because we've accomplished our goal. So I definitely want to return one when sum so far is 100 because we've reached our target. And then in the other case, I want to return zero, indicating that, hey, you should stop recursion, but we've reached a failure case, just like hitting the boundary in the past question. Um, so yeah, I think it should be when the index reaches the end, which would correspond to this. Um, okay. Yeah, probably not the best explanation. I mean, I don't even know if it's right, but this one was a bit more pattern matchy. Um, apologize. I'm just on these for the first time. Slice and dice. Copy equals list. So this is going to make a shared copy, maybe, perhaps. Yeah, I can kind of hint at it. Um, what is this problem? What are you doing? Oh, is this like what would Python do? Okay, so let's make a reminding diagram. We have a global frame. We have a function called slice and dice. It's going to point to a func SND parent equals global, and it takes as parameter a list. Um, and then we define this list. This list points to a three-element list whose first element is the list with zero. The second element is the list with two. And the final element is a empty list. I forget how these things look like. All right. B is going to, you're going to set B equal to the list. But whenever you set a, a variable name to an object, the way I like to think of it is just like, Python's too lazy to say, oh, B equals list. So B, I'm going to go over here and make my own copy of a list. Like that's too much work for Python. Like, Python's kind of lazy. And it's going to point to this existing object in memory. Just a thing you have to remember. And I say objects, not lists specifically. So this is also going to be the same for functions. If I set b equals to slice and dice, then I'm just going to point at it instead of making a copy. Um, so now I want to print 0 in b. Okay, so let's evaluate this expression. Uh, 0 in B is this guy, and the list including 0 is definitely in list, which is what B is pointing at, right? Just match this guy and this guy. So A is going to be true. If I ask if 0 in B, um, it's going to be false because we look at this first element. Are you 0? No, you're not 0. Are you 0? No. Are you 0? So therefore it's false. Python isn't going to do all that work and go recursively search in all of your sublists. You would have to write that code yourself. Python's only going to look at the first level. Yeah, so this is false. True, false. Is B pointing at the same list or different list? List in the global frame. Same list. Is copy pointing at what is copy? Oh, oh shit. I didn't put on this line. Okay, that's okay. So we got these two done. Um, let's not get ahead of ourselves and keep executing this code. So we're gonna have a new list. This is equal to slice and dice. For B and B if B. Oh my God. Okay. So let's see. Slice and dice do. This is a function that is going to make a shallow copy and then return the shallow copy. All right. And then for every element in B, for B in B, I had to do this, man. Okay, so we're gonna iterate through this if the element if B, which this if B expands out to if B is not, or no, it's just like if B exists. So B is of type list. This is a list. If you call bool on an empty list, this returns false, just to say that an empty list is falsy and anything else is truthy. So therefore, uh, yeah, so this just means if it's not empty, so I know that we are not going to iterate to this last element. We're only going to look at the first two. And then for these two items, we're going to call slice and dice on it and construct our new list. Okay, so list comprehension is going to call a function on every item and then aggregate those elements into a new collection. The first element of that is going to be whatever is produced by calling slice and dice on this guy. When I call slice and dice on this, again, since we're making a shadow copy, we're not going to make a brand new, like, we're not going to literally make a copy of it. Okay, so it's going to look like this, basically. How do I know that? You're making a shadow copy of whatever is stored at this current index. What is at this index? A reference to another object. So we are going to store that, we're going to take this reference and we're going to put it in our bucket. And that reference just looks like another pointer. Was that clear? I doubt that was very clear. Like, mm, yeah, basically when you make a shadow copy of a list, you do get a new list. Um, but any object references in that existing list that you copy, we're not actually going to remake that object in memory. So we're not never going to get two of these lists. We're not going to get another 0 up here. That would be a deep copy, and there's no built in Python that will just magically do that for you. You have to write your own code to do that. But when you make a shadow copy, Python does know how to do that. And it's just going to be lazy and reference the existing object in memory. Whereas if there was, in contrast, if this is a primitive, then you would just copy the 3 down. And then the second element is going to be a shadow copy of this. So we have this monstrosity. And then so print new list is B pointing at the same list as still pointing at the same list. Is copy pointing at the same list or a different list than list. In the local frames where slice and dice is called. Ooh, okay, let me think. Okay, so I got kind of lazy. I didn't make all the new frames. So, okay, so technically we would see frame 1. Um, Slice and dice, parent equals global. And then the slice and dice takes the parameter list. And the input for list is each of these B's within B. So these guys. So list is going to point over here for the first iteration. And then it's going to make a copy. And when I make a copy of that list, because it's an object, I'm just going to point to it instead of making a new one. And then I'm going to return it. So everyone in our frame points to this guy. And then finally, we toss this pointer in a bucket. Like we're constructing a new list, right? Through our list comprehension. And I'm going to move this pointer over here and shift it down here. And that's what the list comprehension does. Is copy pointing at the same list or different list than list in the global, than list in the local frames of slice and dice is called. Is copy pointing at the same list or a different list than list in the local frames of slice and dice is called. Same list, reasoning, shadow copy. How many times is slice and dice called? I'm pretty sure the condition gets checked. Yeah, I mean that makes sense. Right? Like even if I don't remember this fact, it just feels more logical for a programming language to probably check before we call. So we're not going to hit the last guy. So only twice. And what does the print new list output? Well, internally there's some weird stuff going on, but when we print that out, the output is just actually just going to look like the same thing. So it's going to just look like this. Okay, because all we did was we took this and we made a copy of it. And the internals are quite complex, but visually, you will see. Oh, wait, except we filtered out the last time, so it's just gonna be the same one too. Number 3, balls. Having been inspired by CS70, Chris and Cedric. Oof, I'm actually really scared of this problem. Chris is very smart. But anyway, Chris and Cedric are playing a game with their N balls in a bin. The game works as follows. Players take alternating. Oh, and Cedric selected to the map. Players take alternating turns. At every turn, a player can choose 1 to M balls to remove from the bin. If there are fewer than M balls, why am I getting a 70 from? So if there are fewer than M balls currently in the bin, players can remove at most the number of current balls in the bin. Player wins if they remove the last balls in the bin. That is, a player loses if it's their turn and there's no more balls, because the opponent removed the last ball. Assuming Chris goes first and Cedric goes second, there are num ways to count the number of ways Chris can win. Chris is player 0 and Cedric is player 1. Okay. So we want to count the number of ways that player 0 can win this game where there are N balls in a bin. Okay, so there's a bin. There are N balls. And player zero and player one are going to come in and take alternating turns. And so let's say we're at turn one, and that's going to be player zero for Chris. Chris can choose one to N balls. What is N? Okay, so M is the inputs. Um, you can take away up to N balls. Is N guaranteed to be less than N? That would make sense, right? Oh, there might be fewer than M balls. Player can remove at most the current number. Okay. So M is always going to be bound by N. This is ball zero, this is ball one, this is ball N. And then Chris can come in here and you can take a one to N balls to remove. But from what position? Just like arbitrarily, just like from the end, from the front. Okay, I don't know. So you can remove. Let's say it chooses to take away one ball. And then turn two, let's say we have Cedric, player one, coming in. He can choose to remove one ball, and then now Chris would win, so this is one way. Um, and then if we, okay, I mean, so I think I get the game. Um, Assuming Chris goes first and Cedric goes second, fill out number ways to count the number of ways Chris can win. All right, so let's solve this just because I need like my brain is not this problem is not clicking right now. Um so there's N balls. And, I don't know why I'm drawing this. Let's draw a bin. There's a bin. There are four balls. And um there are three ways that Chris can win. So Chris can win if he comes in, he knocks out one ball. Let's say Cedric knocks out two, and then Chris wins. Do the different colors. Chris can also win. If he comes in, he knocks out. Okay, so he cannot knock out four balls because he would lose. He cannot knock out three balls because then Cedric would win. But he can knock out two, and Cedric can knock out one, and then Chris has one. All right. You can now remove zero, so I'm actually struggling to see what are the other ways you can. Oh, actually, M was two, so we can't take out that anyway. Oh, I guess are the other ways just like the other balls? Like he could have taken the second one. Like are the balls distinguishable between each other? So, I mean, this definitely exists, right? So we're at three. I don't quite get what. Let's reread. A player takes alternating turns. They can remove one to N balls. A player wins. What is the fourth one? I have no clue, but I think thinking about this problem, you'd hint at, okay, so we have an n, and then we're going to maybe like, well, we can either iterate from the range from 1 to m and try out removing each of those options, or um, we can do a kind of count partition style, parameterized by n comma k, and we can decrement k, representing the fact that we can never use that particular k again. And I feel I gravitate towards that just because okay, because first of all, I don't see a for loop. Actually, never mind. This is the for. Is this a for loop? Uh, yes. This is a list comprehension, so I do need a for. So like maybe this is like from range from 1 to n or something. I need hints. Um, okay, so I'm gonna just try to grab some low hanging fruit. Um, we are ultimately returning a number, so this like this C over here, we can't return like a Boolean value, right? So it's not gonna be all, it's not gonna be any. Some feels logical because we want a total. So I'm gonna just throw this down for now. D, E, and then here is our list comp. So definitely like probably not these two. Actually, we probably do want that just because I'm not sure. Yeah, probably these are better because we actually go from 1 to m instead of 0 to m minus 1. And then we just want to think about if we actually want this gift or not. So A is like the success case. B is the failure case. If player equals 1. Okay. Yeah, so in these kind of game problems where you're alternating between the two, it's common, I'm referencing like um I think in the hog game, right, you ran the while loop, and then every iteration you would change who the player is. I think there was a discussion problem, um, like sevens, discussion 3 maybe. Um, so yeah, it's a common pattern that we're gonna kind of alternate the player to am I recording this? I hope. Okay, I am recording this. Uh, to simulate like the alternating nature. So, for example, D, which is where player is, it's probably going to be whatever like we want to move. If it's 0 right now, then we want to pass 1. If it's 1, we want to pass 0. So D, did it give us options? I mean, if we're alternating players, then what's probably going to happen is like I think there's a formula to switch between 1 and 0s. It's like player minus 1 or something. So like if uh I'll come back to this thought. It's not too important right now. Like here we'll probably need some swapping thingy. And then balls is what is balls? I why did we have this instead of just using n. Okay. And then let's see, the failure case. This is a base case, so probably not the recursion. Um, balls will start at n, so it's going down. So, these like make kind of sense to catch the bottom, and n is less than n. If n is less than, or if m is greater than n, you return zero, probably. I'm also confused because here we pass in player equals zero, sort of signifying that at the very first frame, the very first iteration, player zero is going. So, um, but then in the end, we're saying if player equals one, turn on. Because a player wins if they remove the last ball. So like isn't like the final winning successful turn, shouldn't that be the same player as the player that started? So I'm real confused about that. Oh, or they could be hinting at this line. Like player B, like Cedric loses if it's Cedric's turn and there's no ball, aka Chris wins. So if it's player one's turn, this is player one, and there's no more balls, being balls equal zero, then Chris wins. Is my best guess here. It was just again just the reasoning. The reasoning being, like I had the confusion of if it starts on Chris, then shouldn't the winning turn also end on Chris? But it ends on the other player, which confused me. But hold on, we can still say something about Chris winning by saying something about Cedric losing. Um, is my guess. On the other hand, when would Chris lose the game? Chris loses the game if it's their turn. There's no more balls. So like if like uh so like it would also be like this. Like this would just be a player. It's like the same thing. But we don't need to repeat this because if it were player one, then we would have already hit this. So then it must already be player zero. Um, so it's already implied that this is player zero, so we only have to check this condition. Um, okay, so we got when player zero. Okay, so we've written some code that will return one when player zero wins and returns zero if they lose. So now we just have to be able to aggregate all of the ways they can win. So we want to think about from the perspective of Christopher. What can Chris? So he can again choose to take 1 to m balls. I feel like m is like upper bounded by n, right? Because it says at most the number of current balls. So I feel like the loop should be from 1 to n, anything. But all these are from 1 to m. Oh well. Uh, okay. So, um, the helper, and then it was comprehension. Um, so what is helper? Um, helper of something is equal to number of ways hmm, number of ways that player zero can win given that balls, I'm referring to this one, is equal to the number of balls. And it can choose between 1 and m. Choose something between 1 and m. Okay. Um, but the thing is, at every stage, Chris can always take from 1 to n. Of course, um, unless you know unless there aren't actually m balls in the bin, but the choice always exists. And because of that, unlike some like at the recursive call to competition, like, and then you do like m minus 1 plus f of plus something, right? Or yeah, I can either skip it and not affect the sum, or I can take something, add it to my current total, and uh, keep using that chunk. But here we're not going to use this minus 1 structure because when you do a minus 1, you're saying, hey, in all of the future recursive frames down the line, I never want you to be able to use the current value of n again. The value that I'm going to send down to you is n minus 1, forever discarding n again. Um, so if I'm trying to partition my 10 given pieces of up to 4, I'm going to try the 4, and then at some point I'm going to throw away the 4 and move on to 3. But the point I'm trying to make is that here we never have that concept of throwing away a choice. We always have 1 to m options, which is why I would reason that we're going to loop through 1 to m always, just like number 3 in discussion 4. right. Um, and while we can always choose M, so M will never change, the number of balls will change given on how many we choose to take. So if we choose to take some K number of balls, the current number of balls that we have is going to go down by K. So here, E is going to lower by however many balls we take. Minus five. And then we've basically solved it. We just need to figure out this last bit, this whole player thing. What is going on? Is it still true that we're trying to alternate? So I still do think we need to alternate. Um, no, wait. All right, so if frame one starts, and let's say, player is 0, and then balls is going to be, let's say, 20, and then they're going to try taking away some amount of balls. Okay, so this is going to branch out like this. In frame two, they're going to first try taking away one ball. So we're left with 19, and then frame three, they're going to try to, sorry, these frame orderings are not true. So it's going to go all the way down first. Um, and then they're going to try taking away two balls, and so on. And then from each of these, they're also going to try taking away one, and then two, and then three, and so on. Now the question is, from this frame to this frame, do we want to alternate the player? Yes, we 100% do, because otherwise this player like there's no way for player to ever become one if we are not actually swapping it. So D, we definitely going to need some swapping algorithm. So frame one is going to refer to player 0, but then frame two is going to refer to um, player one, and then the frames are going to successively take away some number of balls, and then we want to basically um, number of balls will become one someday, and then we want to figure out if that day lands on a even frame or an odd frame. If it lands on an even frame, then someone wins. If it lands on an odd frame, then someone else wins. And then the way we keep track of that is we just keep flipping this player back and forth, and then we catch the end, or we enforce conditions at the end to check which frame we ended on, if the explanation made any sense. Like we're gonna keep flipping back and forth between the players, and all I care about is that one day there's gonna be a final frame where balls equals 0, and at that point I just need to figure out who the player is, and if it's one, then player 0. If it's whatever. It's whatever these conditions say. Okay, that is how I reason through this problem. So then we need some swapping algorithm here. So we need a expression that turns one into zeros and zero into ones. I what is the math? I think um, it's like something minus something. Is it one minus player? I think it is. So if player is 0, then 1 minus 0 outputs 1. Whereas if player is 1, then this outputs 0. Yeah. So sorry if you didn't know that. I mean, again, I don't know if this is the answer, but this is probably it. I've just seen this trick before in some classes. I think it's kind of stupid that they enforce you to know this instead of just using one of these. Mm, I don't think we need this. Um, mm. Because all of these are going to return one and zeros someday, right? And then we're going to sum them. And then the question is, do we want to only filter for the frames? Do we want to only filter for the frames whose player is specified to be zero? But the thing is, our whole code is already written in a way that only cares about Chris winning. Like it's only about Chris. And that is the way we've programmed our base cases. The point I'm trying to make is that our function is already tailored to summing number of ways that Chris can win. Um, like we would need to filter it here. We would need an extra filter if like the function was the ways for like both people or something, and then you only want to take a subset of that. But because our function is already coding up the number of ways that Chris can win, there's redundancy if we try to filter it again. Um, but not just redundancy, it wouldn't work. And I'm trying to think of why it wouldn't work, but it just doesn't make sense to me. Uh, because like the only frames that can return one in the first place are the ones where player equals zero. So like, doesn't make sense to add another filter. I think maybe. What is the order of growth of time it takes to evaluate bins in terms of positive integer and? So it's tree recursive, so it's gonna be exponential. I think. Oh no, no, this is a different function. This takes to evaluate bins of n. Oh, don't do part G. Haven't learned yet. Okay, if you say so. Um, but is this? It is recursive. Yeah, it should just be exponential. Basically, just know that tree recursion problems are basically always exponential. Because of this branching thing, right? So like, what is the total number? Well, if I have something that branches like this, and then the question is, the time it takes to evaluate bins is equal to the number of frames that opens up, right? So then the question becomes how many frames open up, and this is equal to some number to the third power, I think. It'd be like sum of I I maybe like it'd be 0 to the third power, or no, it'd be 1 to the third power plus 2 plus 1 to the third power. So there's 1 here, there's 3 here, and then there's 9 here. I don't know. I forget. Something like that. There's a formula and it's, oh, no, no, sorry. 3 is the base. 3 is the base. So it's 3 to the 0 plus 3 to the 1 plus 3 squared, 1 plus 3 plus 9, which matches this. And then that will help you count up the frames. Oh, camel. Oh, camel. Oh, that's a joke. All right. I get that joke. Oh, okay. I don't like that joke. A camel sequence is an integer in which each digit is strictly less than or strictly greater than both of its adjacent digits. Oh, okay. Write a function is that takes returns whether n is a camel sequence. So is this like a hump detector or something? Um, so like 1, 5, 2, 6, 3. All right, so we have like a hump here, have a hump here, maybe. Um, is an integer in which each digit is less than or greater than both of its adjacent digits. Okay, so basically it's really hilly. Every digit has to be smaller than both of its smaller or greater. So this guy's smaller than both. This guy's greater than both. This guy's smaller than both. This guy's. Is this tree recursion? This doesn't feel like tree recursion. All right, any single digit integer is about Camel sequence, so that probably lines up with the base case. I don't think this is tree recursion because you could solve this and the reasoning for that is you can solve this with a for loop, right? So let's solve this with a for loop. It'd be like for I don't know, while and what would you do? So like if n mod 10 or no, how do I check if it's a single digit? If n is less than 10, which means it's, then you can just return true. Otherwise, this whole problem hinges on every digit has to look at its neighbors. Okay, so let's say, yeah, this is iteration 0, 1, 2, 3, 4. Let's say we're on iteration 2 or iteration 3. This iteration has to get the number beforehand and the number afterwards, and then just needs to do a simple comparison. If I am less than both of those numbers, then I will go on to the next iteration and keep checking like that. Because I'm able to solve this problem linearly, just in a single pass going forward, I don't need to think about tree recursion. Because you can solve it in a for loop, you can solve it. Um, and then so the question is, how do we get the last number and the next number? So this is not, we'd actually start again, right? So we're at the 9. We get the 9. But then we have to, so let's say we're here. We have to get these 2 digits. So we know how to get the next digit, right? So 8 is equal to n mod 10. And then 9 is equal to n, chop off the 8 and then mod it, and that gives you the 9. So chop off the 8 and then mod it. So this gives you the 9. This gives you the 8. Then the question is, how do we get the number beforehand? What you can do is in your for loop, you can set like a prev, right? Refer and a next. So at every iteration, your current value is n mod 10. Your next value is n div mod 10. And then the clever thing you can do is you can set your previous value to the current value. And this lets you basically, so in this iteration, we set prev to the current value, which means that in the next iteration, the previous value was the last current value, which is the previous value. If that makes sense. So So this is how we'd work it out in a while. And then so we have an A and we have an incur. Hmm. Yeah, so I was hoping we have access to another one called Brave. That would have made it real nice. Um, but yeah, not sure yet. L if incur. What is incur? Um, hmm. Oh, like increasing or increment? Okay, okay. I see. I see. Oh, okay. Right. Okay. So yeah, incur means increasing, right? Because if it were increasing, okay. So let's say we start here. Um, if we are increasing, then at the next frame, we want to check if the next digit is smaller. So like if increasing, then we want to mandate the condition that cur is less than next and recurse. If decreasing, like we are here, then this too needs to know that it's less than the next number. And I just wrote the same thing twice. So if we are increasing, then my current has to be less than the next. If I'm decreasing, then my current also less than the next. Oh, it's less than the next. Right, so they're saying if I'm already going up to here, then my next one better be less than me. This way I have a hump. If I'm on my way down to somewhere, then at that somewhere, I would want to know that my current value is less than whatever the next guy is. And if it's ever false, then we know we just short circuit and return false, right? But if it is true, then we keep recursing. Okay. But the thing is, where do we get our current our next? Uh, and well, we know how to get current our next. Like over here, this curve is going to be 10, and next is going to be so if it's greater than mod 10. Right here, and then 10 less than, I think. And then again, we use per and x because they don't give us a way to keep track of our previous. We could have if we have a extra parameter here, but otherwise, there's no way to get a number in from the past. I can reach down into my number and get future values, but I cannot get previous values. So given the constraints of this problem, it seems like we're going to just work with current and next. So we're going to work with pairs of two instead of triplets. Okay. So all right. So I'm coming from here. I go up here. So therefore I am increasing. I reach over here and I check if I'm greater than the next one. If I am, then I should keep recursing. So this is going to permit me to go down but now I'm decreasing. So from the next frame, it's like, yep, I'm currently decreasing, and I want to check if the next value is, I want to check if this next value is less than me. And if it is, then we can go up there, and now we're increasing. So from here, I want to check if I'm greater than the next value. And that appears to be the accurate one too. So I think increasing just like a true or false, maybe. So C would be like helper. So if we are increasing and we pass this condition, then we're going to move on to the next zigzag. And once we move on to the next, we are now decreasing. So we're going to flip it. And so the first parameter is n, so this would be the second parameter. And then n, hopefully, don't have to think too hard, just that, I hope. So this just says if a single digit aligning with the base case they gave us. If n mod 10 is, wait, these are all less. Ooh, I messed up. I messed up, didn't I? Okay, so it can't be these. This makes no sense. Like these would always be zero, right? Because this is a single digit, so then 4 divided by 10 is always gonna be zero. These make no sense. Here a 2-digit are always gonna be greater than a single digit. These make no sense. This doesn't. We're not comparing digit to digit, are we? So it's as you set up there, it's gonna have to be these two. I don't think equality is allowed, right? Like it has to be, yeah, strictly less than or strictly greater. So it should just be this. And then the other one's going to be the opposite. And then the other ones are up to us. Um, so let me think, why was I wrong? If we are increasing, start here. 1, 5, 2, 6, 3. Let's start here and I specify that I'm increasing. So I think I'm increasing. So I thinking that I came up from something. So then in order for us to maintain this Camel condition, because I came up, then that means I'm at a peak. And therefore I must also be greater. I want to be greater than the next value in order to maintain a Camel condition. Why is it flipped? Why did they flip it? So they're saying it has to be less. N mod 10 has to be less if I'm increasing. Or I guess they don't, I guess maybe they don't mean increasing from the last value and they're like, I'm going to increase. And if I'm going to increase, then I have to be greater. Oh no, if I'm going to increase, then I only have to be less than my next value. And if that's true, we go on to the next iteration where we now say I'm decreasing. So the 6 thinks it's decreasing down, so it wants to make sure that it's greater than this. And then we flip it. So the 2 thinks it's increasing up. Or the 2 is like, I want to increase. And therefore to increase, it has to be less than. Yeah, I was just kind of off by 1, if that makes sense. So C is going to be, so both of these, we're just going to cut down 1 number. This is C, comma, not increase. And this is going to be, oh, they're the same. Yeah, because this is a condition that, oh, I guess, do we have to go digit by digit or can we go like 2 digits by 2 digits? I mean, because we're only comparing pairs, in order for us to, like, we have to check this pair and then this pair, and then the combination of those two together forms a camel. Whereas I think if we go by twos, like we go here and then we go here, but then that doesn't maintain connectivity between, or like we're not able to enforce anything about the relationship between these two. So it feels more natural to just go with our current approach. Um, and yeah, I mean, if you had time, I would probably try an example, just to prove it's correct. Um, and I think the F and G just saying like, hey, um, we can either start at a peak or we can start at a trough. Um, like we can either start going up or we can start going down. So we need to consider both of those possibilities. And we know that the camel sequence is either. It doesn't care if we start high or start low. Just needs to care about the zigzag. So here we're just saying it could have been either of these two. This would be like helper of n true for increasing, helper of n false, and I'm assuming the order just matters. Yeah. Right. Uh, yeah. Thank you. I'll probably check how I did now. I'm just gonna add head. Actually, I'll just look at it and then I'll put comments for corrections. Uh, thank you. Sorry if it's wasn't the most clear in teaching it, and then also sorry if I kind of flew at the last one just because I've actually seen or written a similar problem. So okay, hope that helps.